Hi, I'm Addison. Today we are going to talk about timing algorithms. The difference between a fast algorithm and a slow one is literally how long each algorithm takes to execute. While this may be obvious, there is a minefield of bullshit about timing algorithms, but an old expression from motor racing addresses the situation properly. When the flag drops, the bullshit stops. With the choice between the clock and endless blah blah, the clock beats the blah blah every time. Now, while there are a plethora of different methods to time algorithms from sophisticated to downright crude, the operating system happens to throw a spanner in the works on a regular basis because of it having a higher privilege level. Intel x86 and x64 hardware provide a hierarchy of privilege levels, which allows the operating system to maintain full control while providing a user level of access for running applications. They are respectively Ring 0 for the operating system and Ring 3 for application. This affects timings, no matter what technique is used, and it affects all techniques by the same amount. Now, in the range of techniques that can be used to time algorithms, some are that complicated that neither the author nor the user have any method of testing the accuracy of the technique. Then there is the gee whiz factor about how clever the technique is and why it is politically correct and should be used based on the perceived status of the author. No matter what technique you use, it will get pushed aside whenever the operating system takes priority. The viable alternative is a method that is crude, unsophisticated, has terrible granularity of about 16 milliseconds, but it is simple and clear: the Windows function get tick count. It does, in a clear and understandable way, produce a result in real time. It needs to be used in a particular way. Each test needs to be run long enough to reduce the level of granularity, in most cases about 1 second or a bit longer, and the test needs to be adapted to the task that the algorithms will be used for. We will address that factor a little later. This is the simple basics of using get tick count. 2 function calls with the test in between then, and you subtract the result of the first from the second to get the duration in milliseconds. Now, to improve the accuracy of the results, setting the priority class higher reduces interference from other running applications. When the timings are finished, you reset the priority class back to normal. This can be further improved by using the instruction CPUID, which is a serialized instruction. From the Intel manual you get the following.
CPU ID can be executed at any privilege level to serialize instruction execution. Serializing instruction execution guarantees that any modifications to flags, registers, and memory for previous instructions are completed before the next instruction is fetched and executed.
The last thing we need to do to trim the accuracy of the timing method is to pick the start of a time slice, and this is done using the Windows function sleepx. Sleepx is in fact a very low-level function that uses the CPU's timing method to force a process, the running application in this instance, to yield for a specified duration. Once the yield duration has expired, you get the best chance of getting the start of a time slice at its beginning, and this improves the accuracy of the timing. Assuming that the higher priority class has been set, we now sketch out the basics of how to time an algorithm. We make the calls to CPUID and sleepx to stabilize the timing as far as possible. Next we call get tick count to get the first time result and store the result in a protected system register, R12. We set the loop counter in the R13 register, then drop into the algorithm being tested, which is run with the number of iterations set in R13. Once all of the iterations are completed, we get the time from get tick count again, and subtract the first call result from the second one, R12 from RAX, and you have the millisecond result in the RAX register. Now, something we need to discuss: different algorithms require different testing methods, depending on what they are going to be used for. The difference can be characterized as attack versus sustain. For very short algorithms that only process small amounts of data each call, The attack factor is the one you are after here. This means testing on a small amount of data and calling it a large number of times to get the duration up to a reliable level. This is where having no stack frame and very low instruction counts matter. For an algorithm that is designed to process very large amounts of data, you use a rather crude technique. You allocate a large amount of memory for the data to be processed, fill it with whatever data you need to process, and then run the algorithm to process that data. What you require here is sustain, and to get the timing long enough to be reliable, you will have to make the test data long enough to get up to the duration you require. Between the two extremes with many variation in between, you can tune your timing to best suit the algorithm design you wish to optimize. Before we go, we have a short message from Old Father Time.
I am time. Ignore me at your peril. I have no beginning, and no end. I never sleep, I never stop. Ignore me and your algorithms will run like crap.
That is all we have for you today. Check out the example code for this video. It tests two very similar unrolled algorithms and allows you to adjust the rate of unroll to see how it works. See ya next time.